All right, so take a few minutes here and just kind of walk through essentially everything that we've covered in this course. Just a quick look at all the formulas and processes and whatnot without too much detail. So we'll start here with tests and intervals. First thing you want to make sure you do is either name the test or the interval, and there's all the different names. The one that's not sitting in here, and it's just a very specific version of a one sample test, and that would be um, matched pairs. And so we'll kind of talk about that as we go through here. Remember the difference between a T and a Z is whether or not you're given sigma or S. Sigma will tell you it's a Z. Again, if you're given sigma, it's a Z test, or if you're given S, the sample standard deviation, you use a T test. So you have one proportion and two proportion tests, one sample and two proportion Z tests, which are for means, and then you got chi-squared and T test for slope. And then there's your intervals on the other side. Again, you could also do an interval for slope. We'll just kind of walk through all the different steps for testing. So remember with hypotheses, it's always a parameter, right? It's always a parameter. And then this is going to be equals, greater than or equal to, less than or equal to. And this is also a parameter. And remember that the parameters that we use are mu, p, or beta. And just good chance to remind you here, the statistics would be x bar, p hat, and then the slope b. So we're always going to use parameters there. And then this would be not equal to, greater than, less than. And if it is a two-sample test, remember it's going to be mu1 versus mu2, or it could be p1 and p2 when you're going through the processes. But usually, if it's a one-sample test, it's going to be a number versus two-sample. You're comparing mu1 to mu2. Just be sure to label your populations. Now, all the conditions. This is probably where most of us want to make sure we're, if anything, this is probably where you're shaky. So go ahead. All of these are random, very first. If it's a two sample, they're both random, right? Both random. Random for means. I'll just go ahead and put random for everything, right? Chi-squared, we want random, right? And you might just mention SRS. So for proportions, the first, for one sample, we need the population, excuse me, we need the population to be bigger than 10 times your sample size. And here it's both populations are greater than 10 times N1, 10 times N2. Then we have NP and NQ greater than or equal to 10. And here you just have to break it down, N1 times P pooled, and then N1 times Q pooled, and then also N2 times P pooled, and N2 times Q pooled. All those have to be greater than or equal to 5. Um, I know it's kind of hard to read those, but again, those are for my pooled values. Excuse me, I kind of messed up right there. Let me clean that up just a little bit. That's not P times Q, that's uh, P pooled for both of those. So that's a small p. And I apologize for being so small, but just trying to get it all on one page. So again, for proportions, random population is greater than 10n, and then we got NP and NQ greater than or equal to 10 for one sample, greater than or equal to 5 for a two sample. And remember, you test the pool, and you pee in the pool, all that good stuff. Any of the two sample proportions, two prop z tests, you're gonna want to use that p pooled value. So for means, really the biggest two issues, we want random and we want large. So it's either n is greater than 30 or it's normal. And here, we want the two groups, again, we want n1 greater than 30, n2 greater than 30, or again, we want to make sure we have normal. The third condition here, kind of ran out of room there, we want to make sure they're independent of each other, and that is the groups. If the groups are not independent, right? If for whatever reason, if we have two samples and the groups aren't independent, pre-test, post-test, I'll go ahead and make a note here. If group's not independent, that means that we're looking at matched pairs. And then you're worried about individuals being independent. Individuals independent instead of the two groups, right? And it's at that point that you'd run a one sample test on the difference, like that L3. All right, so chi-squared test. The other condition here is we want all expected values greater than 5. That's the easy one, greater than or equal to 5. And I wouldn't worry too much about anything else. The slope test, again, we want to make sure data is linear or roughly linear. And that's just look at the scatter plot. We want to make sure we have randomness. And then these last two, really, I'll go ahead and put these together and say that we have a good residual plot. And again, a good residual plot is basically just going to push us toward, hey, data is pretty much linear. Writing the formula with symbols. So really, that's just your test statistic, Z or T, equals observed minus predicted over the standard deviation. And that big list of standard deviations it's given to you on your formula sheet. And then you also have chi-squared, which is the summation. Don't forget that. Observed minus predicted over observed. Excuse me. So fill in the formula, do all the right mechanics. Remember your test statistic. It could be a Z if it's a Z test, a T if it's a T test, or chi-squared for a chi-squared test. Write down the p-value. Make sure that you put this p-value, the inequality, right? P is greater than alpha or P is less than alpha. The typical alpha is 0.05. Remember, if P is less than your alpha level, you'll reject the null. And then if P is greater than alpha, you fail to reject the null. And make sure you use context and you answer the question when it comes time for the conclusion. Right? Make sure you don't just put evidence suggests that the true proportion is this. Evidence suggests there is a difference. Make sure you answer the question. Sometimes I'll say something about students are curious if they are correct. Make sure you address whether or not the students were correct. With confidence intervals, really a lot of this is the same. Your conditions are pretty much the same except with proportions. With proportions, go ahead and use p hat instead of p. But really everything else is the same. You write your formula with the symbols. Again, if it's a means problem, it's x bar plus or minus your z or your t star, whichever one of those, times sigma over the square root of n, and sigma could also be s, whichever one is appropriate, whether it's a z or a t interval. And then for proportions, right, we're using p hat. P hat plus or minus, this will always be a z star, and then p hat q hat over n, always the case. When you're getting that z or the t star value, remember we get those from the table. Z star is the last row on the table typically. Make sure you just show that you can do the right work. You plug things into the right place. You're going to let the calculator do the work and then get the correct interpretation. Again, there's the way you can start off every one of those, depending upon your alpha level or your confidence level. 95% confident that the true proportion, that the true mean, that the true difference in means. Remember, and if it's a two proportion or a two sample t or z interval, 0 is the critical value, right? Is that key number, right? If 0's in the interval, there is no difference. If 0's not, if it's all positive, it tells you something. If it's all negative, right? Margin of error typically used when you're going to be asked to find a sample size. And that's right here with confidence intervals, because if you'll notice, this is just that last part of the confidence interval, right? You would use z star sigma over square root of n if it's a means problem. And here we are, if it's a proportions problem. You'd use z star times the square root of p hat q hat over n. The most conservative proportion is 0.5. And typically when you would use p hat versus the 0.5 is is a p-hat given? If they're asking you to find sample size and they don't give you a p-hat, first, make sure it's a proportions problem. Second, if they don't give you a p-hat, you use 0.5. And a lot of times, too, the context of the problem will help you out there. Best way to reduce margin of error, increase sample size. Bigger sample size fix so many problems in this course. So anytime you need to fix something, increase your sample size. The other way to reduce margin of error is also to increase alpha, right? Keep in mind, a 95% confidence interval is more narrow, is more narrow than 90%, right? I can be more confident if I make it a bigger interval, right? I'm 100% confident that between 0 and, 80 of you guys will all make 5s, right? I can be confident with a huge interval like that, but I'm not going to be as confident as things get smaller and smaller. Degrees of freedom, this is good to remember. If it's a 1 sample t-test, it's going to be n-1. 2 sample, the calculator will tell you. It's a weird formula, so you're just going to let the calculator do the work. Chi-squared, remember that's rows minus 1 times columns minus 1. And then if it's a t-test for slope, it's going to be n-2. All right, so we'll flip to the back. Some of the stuff we talked about before the break, before we started doing all this inferential statistics. Experiments versus observational studies. Experiments always have treatments assigned. Right? Experiments should also have some type of control group. That's another good indicator that you're talking about an experiment versus a study. Why use randomness? The biggest reason is to reduce any kind of bias that could be introduced by the person doing the experiment. It could be to reduce bias that could be introduced by the subjects that are in the experiment. One of the things we talked about within experiments was the idea of blocking, and this is to reduce the effects of a lurking variable, of a lurking or a confounding variable. All right, keep in mind, right? One of the good examples here, if we wanted to do a study on dog food and how effective it is in terms of helping dogs put on weight or maintain a healthy weight, it'd be important because different breeds of dogs obviously respond differently. Maybe we block by size of the dog or breed of the dog to help reduce some type of lurking variable, maybe associated with dog size or whatnot. Types of samples that we might do, simple random sample. This is where everyone has an equally likely chance. Everyone is given a number, and you pick random numbers. Whether it's a table, whether it's you got your random number generator. Stratified, you separate into groups. Excuse me, if I could spell separate. You're going to separate into groups by some type of category. Easiest way to think about this is, at the high school, and you do an SRS within the group. So we'll separate into, each class, freshman, sophomore, junior, senior. Then we'll randomly pick 25 of each. That ensures that every group is represented. A cluster sample, you randomly select a group, and then survey, study, measure every individual in group. So this would be like, we'll go and we'll randomly select a class, room 204. We'll randomly, if room 204 is randomly picked for our survey, then we have to talk to everyone in that class. The worst possible way to do a sample is convenience, and that's just really whoever, whatever. So maybe we'll get rid of whoever. Whatever is closest, or really, you hate to use the word to define the word, but whatever is convenient. That's a convenient sample. Talking about interpretations of some of these big terms, coefficient of determination, again, that's r squared, and that just says blank percent of the variation in y is explained by the linear model x being the explanatory, y the response variable. Slope for each 1 unit increase in x, y increases or decreases depending upon the sign, by the value of the slope. The y-intercept tells us that when x value is 0, y is whatever that number is. Remember, it may or may not have a practical meaning. Interpretation or meaning. All right. Standard error, if you want to think about this, this is the big list of all of those standard deviations. It's the standard deviation for each of our different types of tests, but really at the end of the day, it's just how far the typical observed value is from the mean. A residual, remember, there's a formula that we saw in the reviews, is observed minus predicted. And then one way to think about that, it's really just the vertical distance, especially with this bivariate data, from an observation to the least squares regression line. How far away from our predicted value is an observed value? All right. And then the final column, go back up to the top, probability. Two things are disjoint if there's no overlap, no common experience. You might also see this referred to as mutually exclusive. All right. Independent, one won't affect the other. All right. We had a formula for that. The probability of A given B has occurred has to be equal to the probability of A. That tells you if two things are independent. And just very quickly, again, that conditional probability of A given B equals the probability of A and B over the probability that B has occurred. Right? And independence is important if you ever want to use the multiplication rule. But again, we've already seen that. We've already discussed it. This is just a quick review. Binomial is a situation that occurs when there are only two possible outcomes. Yes, no. Win, loss. The binomial PDF, if you're going to use that in the calculator, the syntax will be N, P, and K. And what that is, you would use that, the probability that x equals 2. We flip a coin 5 times, and if we had exactly 2 heads, right? So if we want the probability that we get exactly 2 heads on 5 flips. So our binomial PDF here, because there's only 2 options, heads or tails, we'd have a total of 5. The probability is 50-50, and we want 2, right? CDF would be, again, same process, but this would be, what if we said, what's the probability that we get no more than 3 heads? Now, here's the thing, binomial CDF, not a ton of room, it always uses less than or equal to every time. Every time. So, if we end up with a situation, what's the probability? This would also be the same thing, probability x is less than 4. You always have to figure out a way to take care of this in the calculator. The mean of a binomial, this is a situation that's given to you. That's just n times p. And another way to look at mean is expected value. And then standard deviation of a binomial is n times p times q. Geometric setting, that's until we have success. So in our situation, we could say, what's the probability it will take 2 flips until heads, right? So what that means, if you're going to use the calculator, so for us, that would be the probability that x equals 2. When you're typing it in terms of syntax, it's the probability followed by the number you want. So for us, we would type in so the probability of heads is 0.5, and then our success is at 2. CDF is continuous, so that would be like the probability of at least 2 flips until success, until heads. And again, this is always going to be P then K, but it again always uses less than or equal to. So if you'll, for more detailed example, if you'll look at the video involving binomial and geometric distributions, there's what that would look like as a probability statement. But there's better examples as you look at that particular video. Random variables, this is where we set up the tables. Remember, the probability is always summed to 1. And if you ever have to combine random variables, right, the expected value of 2 different variables all together, remember, that's just the expected value plus the expected value. But if you have to add standard deviations, remember you always add variances. And so again, for a more detailed example or two of that, if you'll look at that particular video. And then finally, this is kind of unit 1. As you can tell, we've been kind of working backwards through all this, but the univariate data, if you have to describe it, so we have shape, outliers, center, and then spread. Remember shape, you got mound versus uniform, unimodal, and you got bimodal. You can call things relatively normal, and then you got symmetric or skewed. Remember, skewed left would mean most of the data is to the right. And then skewed right means most of the data to the left. So this is skewed left. And this is skewed right. Okay. And then if you have to describe bivariate data, a scatter plot, we want positive linear, or positive negative, excuse me, linear, nonlinear, strong, moderate, weak. Some good examples of that on that particular data set. And then whenever you're asked to compare 2 data sets, make sure you use comparisons. The mean here is bigger than the mean there, right? If you're ever describing the centers, right? The 2 most common would be mean and median. If you're talking about spread, this range is larger than this. You could also discuss standard deviations, one of the common ones. And then one thing to throw up here is outliers, 2 or 3 standard deviations, or the 1.5 IQR rule also comes into play with outliers. So make sure you're aware of how to do both. Again, more detailed examples in all of the smaller videos going through each of the review sheets. But this is kind of everything that we've discussed in here. And if all this stuff makes sense and you can do the examples, you're on your way.